4.5 Lesson 1, Derivatives of Inverse Trigonometric Functions. So if you look at our vocabulary, we're reviewing some things that you learned in algebra. What is a relation? A relation is a set of ordered pairs. Here's an example of a relation. I have a set of 4 ordered pairs. Each ordered pair has an input. These are coming from the domain of the relation, and there is a corresponding output, which are coming from the range of the relation. And then we have the vocabulary term function. What is a function? Objective 1. You will know that a function is a special type of relation such that for each input there is exactly one output. So for the example that I have here, this is a relation because it is a set of ordered pairs, and it is also a function because for each input there's exactly one output. So when the input is 1, there's no other output except for 10. When the input is 2, there's no other output except for 20. When the input is 3, there's no other output except for 30. A function is a special type of relation such that for each input there's exactly one output. One-to-one functions have inverse functions. This is an example of a one-to-one function. For each output, there is exactly one corresponding input. That's what makes a function one-to-one. One-to-one functions have inverse functions. What if a function is not one-to-one? What might that look like? F of x is equal to x squared is a function. For each input, there is exactly one output. However, it is not a one-to-one function because it is not true that for each output there is exactly one corresponding input. For example, when the output is 4, you can have 2 different inputs. So it's not a one-to-one function. It will not have an inverse function. Because what's an inverse function? It would undo the work done by the original function so that the ordered pairs from the original function would be reversed. And what happens if I were to reverse the ordered pairs from this table? I will get the following. And in the table that I get, you can see that I don't have a function because I don't have that for each input there's exactly one output. For example, when the input is 4, I can have 2 different outputs. So this is a function, but it's not a one-to-one function, so it does not have an inverse function. However, what if I were to erase half of the parabola? Then I get rid of these ordered pairs. And on the restricted domain from x greater than or equal to 0, on this restricted domain where x is greater than or equal to 0, the function is one-to-one, and it will have an inverse function because I would no longer have these 2 ordered pairs. And the inverse function on the restricted domain would be f inverse of x is equal to the positive square root of x. The graph of that inverse function is right here. And you can see that the graphs of the 2 functions are reflections of each other in the line y is equal to x. So that is to help you understand that one-to-one functions will have inverse functions. However, if a function is not one-to-one, you can restrict the domain of the function to make it one-to-one on the restricted domain so that on the restricted domain it will have an inverse function. So objective 3, you will know that the trigonometric functions are not one-to-one. However, their domains can be restricted to make them one-to-one so that they will have inverse functions on their restricted domains. So let's take a look at some examples. So here we have the graph of y is equal to sine x. And you can see that the graph fails the horizontal line test. There's more than one point that passes through a horizontal line that you draw through the graph, which means it's not one-to-one, and therefore it does not have an inverse function. You can see that the function y is equal to sine of x is not one-to-one just by looking at these ordered pairs that belong to the sine function. So we don't have that for each output. There's exactly one input. So for the output 0, you can have many different inputs. The sine function is, of course, a function. Because for each input, there's exactly one output. However, it is not a one-to-one function because we don't have that for each output. There is exactly one corresponding input. So the problem is this. When you reverse the ordered pairs to try to define an inverse function for the sine function, here's the problem that you run into. You don't have that for each input. There is exactly one output because the original function was not one-to-one. So for the input 0, you can have many different outputs. So the sine function does not have an inverse function because the sine function is not one-to-one. However, we can restrict the domain of the sine function so that we're only looking at a portion of the sine curve. And on that restricted domain, the sine function would be one-to-one and it would have an inverse function. So the question is, how should you restrict the domain of the sine function? We want to go about it in a particular way, and this is the conventional way of doing it. You want to have the restricted domain either centered at 0 or be close to 0. So in the case of the sine function, it is centered at 0. And you want to have the restricted domain so that the entire range of the sine function is covered. So the range of the sine function is from -1 to +1. And when you restrict the domain of the sine function to be from -π/2 to +π/2, the entire range of the sine function is covered. And on this restricted domain, the sine function will be one-to-one, and therefore the sine function will have an inverse function on the restricted domain from -π/2 to +π/2. So if you take a look at these definitions of the inverse trig functions, here's what you'll see. Y is equal to the inverse sine of x if and only if sine of y is equal to x, and y is an element of this closed interval, corresponding to the restricted domain of the sine function on which the inverse sine function is defined. An alternative way of writing the inverse sine function as y is equal to arcsine of x, they mean exactly the same thing, and what they mean is this. Y is the angle between -π/2 and +π/2 whose sine is x. For example, if you have y is equal to arcsine of 1/2, you're looking for an angle between -π/2 and +π/2 whose sine is 1/2. And that angle would be π/6 because sine of π/6 is equal to 1/2. Therefore, arcsine of 1/2 is equal to π/6. So what that means is, let f of x be equal to sine x. So we know that sine of π/6 is 1/2. So the ordered pair π/6 1/2 belongs to the function f of x is equal to sine x. So the reverse ordered pair, 1/2 π/6, must belong to the inverse sine function. Let's look at another one. What if we have y is equal to arcsine of 1? What is the angle between -π/2 and +π/2 whose sine is 1? The angle is π/2 since sine of π/2 is equal to 1. So what that means is, for the sine function, we have the ordered pair π/2 1, So for the inverse sine function, we have the ordered pair 1 pi over 2. Here's another one. Y is equal to arcsine of square root of 3 over 2. So the question is, what is the angle between negative pi over 2 and positive pi over 2 whose sine is square root of 3 over 2? And that angle is pi over 3, since sine of pi over 3 is equal to square root of 3 over 2. So what that means is we have the ordered pair pi over 3 square root of 3 over 2 belonging to the sine function. So the reverse ordered pair square root of 3 over 2 comma pi over 3 belongs to the inverse sine function. So we just went over one example where we took the parent sine function and restricted the domain of the parent sine function so that on the restricted domain the parent sine function became 1 to 1, and then we were able to define an inverse sine function. So how do we find the derivative of the inverse sine function? We want to find the derivative of the inverse sine function. So here's what the inverse sine function means, as we just went over. This is the definition of the inverse trig functions. So y is equal to the inverse sine of x if and only if sine of y is equal to x, where y is an element of this closed interval. So when you want to take the derivative of y is equal to the inverse sine of x, you understand what this means. It means y is the angle between negative pi over 2 and positive pi over 2 whose sine is x. So what that means is you can rewrite the inverse trig function as follows. Y is the angle whose sine is x. So sine of y is equal to x. That's what the inverse trig function means. So now, to take the derivative, we want to find y prime. We want to find y prime, which is what we're after, or dy dx. Y prime is the same as dy dx, different ways of writing the same thing, different notations. So how do we find the derivative of the inverse sine function? We're going to differentiate both sides of this equation with respect to x. So we have the derivative with respect to x of sine y on the left side of the equation, and the derivative with respect to x of x on the right side of the equation. Later you will learn something called implicit differentiation. That's what we're doing right now. So how does this work? On the left side of the equation, you will see that we're taking the derivative with respect to x of sine of y. So you have sine and you have y. We know what y is, but we're going to see this as a composition of two functions where the inside function is y and the outside function is sine. So to find the derivative here, we will use the chain rule. So the chain rule says to find the derivative of a composition of two functions, you begin by taking the derivative of the outside function, evaluated at the inside function. So the derivative of sine is cosine, so I have cosine of y, and then I multiply by the derivative with respect to x of the inside function y. And on the right side, I just have 1. So on the left side of the equation, we use the chain rule. And what is this? That's what we're after. That's dy dx. That is y prime. That's the derivative that we're after. So we can either write y prime or dy dx, and that's equal to cosine of y. And that's equal to 1. So we can solve for y prime. Y prime is equal to 1 over cosine of y. So you might think we're done, but we would like our derivative to be in terms of x. Right now you have y prime as a function of y, you want y prime as a function of x. So how do we do that? We're going to draw a right triangle using what we have here. We have sine of y is equal to x. So remembering right triangle trigonometry, this is what you're going to draw. You're going to draw a right triangle. We have the angle y, and remember SOHCAHTOA. So we have sine of the angle y would be opposite over hypotenuse, and so we have sine of the angle y is equal to x, which you can write as x over 1. So here's the angle y. Sine of y is opposite over hypotenuse. So from the angle y, this would be the opposite side. And here we have the hypotenuse. And this is the adjacent side. So what is the length of the adjacent side? We need that to be able to find cosine of y, because cosine of y is adjacent over hypotenuse. So if we can find the length of the adjacent side, we'll be able to write cosine of y in terms of x. So you're going to use the Pythagorean theorem because you have a right triangle here. So we'll label the length of the adjacent side as a. So we have a squared plus b squared is equal to c squared. And b is of course x, and c is of course 1. So now you can solve for a. A squared would be 1 minus x squared. So a would be equal to the square root of 1 minus x squared. So that is the length of the adjacent side. And now that we know this, we can use right triangle trigonometry. Once again, you have the mnemonic device SOHCAHTOA. So we have cosine of y. Here's the angle y. And cosine of angle y would be the ratio of the length of the adjacent side to the length of the hypotenuse. So what I can do is I can replace cosine of y with adjacent over hypotenuse. And the length of the adjacent side in my right triangle here is the square root of 1 minus x squared divided by the length of the hypotenuse, which is 1. So this is, in fact, the derivative of the inverse sine function. So we just proved this differentiation rule. For practice, you will be asked to prove a similar differentiation rule for the inverse cosine function. And then tomorrow we'll take a look at the proof of the differentiation rule for the inverse tangent function. And for practice, you will be proving the differentiation rule for the inverse cotangent function. And you will notice that they are also the inverse secant and inverse cosecant functions, and they also have their differentiation rules. So today we looked at some vocabulary. What is a relation? What is a function? We looked at what it means for a function to be one-to-one, and we understood that that was a requirement for a function to have an inverse function. We also saw examples of functions that are not one-to-one, but if you restrict their domains, they become one-to-one on the restricted domains, and an inverse function can be defined on the restricted domain. The 6 trig functions have that situation, where they're not one-to-one, but you can restrict the domains so that they become one-to-one on the restricted domains, and then you can define the inverse functions on the restricted domains. And we looked at a particular example, the sine function. We restricted the domain of the sine function to be on the interval from negative pi over 2 to positive pi over 2. On that restricted domain, the sine function is one-to-one. We defined the inverse sine function. We looked at the definition. We worked with the definition, looked at a couple of examples of values of the inverse sine function and what they mean. And then we used that understanding and the definition of the inverse sine function and a procedure called implicit differentiation to come up with a differentiation rule for the inverse sine function. And your homework for tonight, you will do the same for the inverse cosine function, and tomorrow we'll look at the inverse tangent function and how to define it, how it's defined, and then how to find the derivative of it.